Here we'll talk about cyclic quadrilaterals, which are quadrilaterals whose four corners, or vertices, are all on the same circle. So here's a circle, and here's an example of a cyclic quadrilateral for this circle. Notice that all four vertices are on the circle. Now there's a special property of all cyclic quadrilaterals that we'll be exploring in this lesson. But first, take a look at this red arc over here. What's the approximate measure of this arc? And if you'd like to review instead, click down here. Great! So it turns out that this arc measures precisely 140 degrees. One way to see that is to look at its central angle, which also measures 140 degrees. So looking at our cyclic quadrilateral again, notice that this angle down here is an inscribed angle for the red arc. So then what's the measure of this angle? And click over here if you want to review how inscribed angles are related to arcs and central angles. Excellent! So this angle measures half of 140, or 70 degrees. Now notice that this 140 degree arc is the minor arc between these 2 points. Let's highlight the major arc in green. So what's the measure of this major arc? Nicely done. So this major arc measures 360 minus 140, or 220 degrees. And that's also the measure of its central angle. Next, you might have noticed that this angle of our cyclic quadrilateral is an inscribed angle for this green arc. So then what's the measure of this inscribed angle? Right, this angle is half of 220, or 110 degrees. So if you look at these two opposite angles in the cyclic quadrilateral, they add up to 180 degrees, meaning they're supplementary angles. Let's see if we can prove that every pair of opposite angles in cyclic quadrilaterals are supplementary. So let's sketch another cyclic quadrilateral. And now pick any of its four angles whose measure we'll call x. Then we'll try to figure out the measure of the opposite angle. Great! So let's call the measure of this angle x. This is an inscribed angle for this red arc over here, which means this arc has measure 2x. And because the arcs in a circle add up to 360 degrees, that means this green arc has a measure of 360 degrees minus 2x. And this green arc is inscribed by this angle over here. So what's the measure of this inscribed angle? Right, so this angle is half of 360 minus 2x, meaning it's 180 degrees minus x. So given any angle in a cyclic quadrilateral, you've just proven that the opposite angle is supplementary. Nicely done. Now it's time for you to make your own cyclic quadrilateral. You can move the vertices by dragging these four yellow dots around the circumference of this circle. The four angles are also shown up here, and you can make sure that pairs of opposite angles like these two and these two are always supplementary, meaning they add up to 180 degrees, or a straight angle. So when you're ready, see if you can make a cyclic quadrilateral that's also a parallelogram, meaning both pairs of opposite sides are parallel. Well done! Here's another example of a cyclic quadrilateral that's also a parallelogram. Notice that these two sides are parallel and that these two sides are also parallel. Now another feature of parallelograms is that opposite angles are congruent, meaning they have the same measure. If you want to work through a proof of this, then just click over here. So that means these two angles are congruent and these two angles are also congruent. And because this is a cyclic quadrilateral, that means these pairs of opposite angles must also add up to 180 degrees. So then what has to be the measure of each of these angles? Precisely. If we say this angle has measure x, then because this is a parallelogram, this angle also has measure x. Since they add up to 180 degrees, that means x plus x, or 2x, equals 180. Or x equals 90. So you've just proven that a cyclic parallelogram must also be what other kind of quadrilateral? You've done some excellent work here. Our biggest finding in this lesson was that in every cyclic quadrilateral, the opposite angles are always supplementary. So for your final challenge, try using this fact to find the measures of the two missing angles in this cyclic quadrilateral. Here we'll discover a property of intersecting secants. So first, here's a circle, and let's draw in two secants, which are lines that pass through 2 points on a circle. And here's where these two secants intersect. Let's take a closer look at these line segments. Suppose this yellow one between these 2 points has length 4, this orange one between these 2 points has length 5, and this blue one that runs from this point all the way over to the intersection has a length of 12. There's a special rule for intersecting secants that you can use to find the length of this green segment between this point and the intersection. To discover this rule, click over here, and if you definitely already know it, then go ahead and solve for this length. Great, let's get started. First, we'll draw in another segment connecting these 2 points and a segment connecting these 2 points. So notice that we have a cyclic quadrilateral here, meaning a quadrilateral whose 4 vertices, or corners, lie on the circle. Now the opposite angles in every cyclic quadrilateral, so these 2 angles and these 2 angles, are always supplementary. So if this angle up here has measure x, then what's the measure of this opposite angle in terms of x? And to review the angles in cyclic quadrilaterals instead, click over here. Precisely, this angle measures 180 degrees minus x. And now take a look at this angle over here, which is also supplementary to this 180 minus x angle. In terms of x, what's the measure of this angle? Nicely done. So this angle also measures x. So no matter what measure this angle has, this angle will always have the same measure, meaning they're congruent. So let's give them the same color. Next, let's look at these 2 angles. Suppose this one measures y. Then using what you know about cyclic quadrilaterals again, find the measure of this angle in terms of y. Great, so this angle measures 180 degrees minus y. And so what's the measure of this angle over here in terms of y? Right, this angle also equals y. So these 2 angles are also congruent, so let's give them the same color. Finally, let's label this angle over here where the secants intersect. Now we have 2 triangles here with matching angles. This smaller triangle with orange, blue, and purple angles, and also this larger triangle which also has orange, blue, and purple angles. To make this a little clearer, let's separate these 2 triangles. They really do have matching angles. And what word describes triangles with 3 matching angles? Precisely, so these 2 triangles are similar, and that means their sides are proportional. So let's call the length of this green segment x. Then the ratio of the 2 sides from the smaller triangle, 4 and 5, must equal the ratio of their corresponding sides from the larger triangle, 12 and x. See if you can solve this equation for x. Nicely done. So x equals 15, meaning this segment must have a length of 15. Again, that's because you proved that these 2 triangles are similar. In general, you can always construct 2 similar triangles from intersecting secants. Next, let's rearrange this equation. We can multiply both sides by 5 and then multiply both sides by 15. So now this says that when you have intersecting secants, if you multiply the 2 segments between the purple intersection and where the secant hits the circle for one of the secants, that equals the product of those segments from the other secant. And this is true for every pair of intersecting secants. Next, take a look at these 2 secants. Suppose these colored segments have lengths of a, b, c, and d. Then which 2 of these expressions over here must be equal? Now with this interactive, you can pick any 2 secants you want by dragging this point outside the circle and these 2 points that are on the circle. Check for yourself whether the products of these segments are always equal to each other. Okay, now what happens if we make one of these secants a tangent? Remember, a tangent is a line that touches a circle at exactly one point. So as we move this secant over, getting closer and closer to a tangent, the lengths of these two segments are also getting closer and closer until they're exactly equal at the tangent. But this property you discovered about secants still works. The product of these segments is still equal to the product of these segments. Now suppose a point on a secant line is 4 from the closer intersection with the circle and 9 from the farther intersection. Then how long is a tangent line connecting this point to the circle? So to review, if you have intersecting secants with segments of length A, B, C, and D, then the product of the segments between the circle and the intersection for one secant equals the product for the other secant. But suppose one of these lines is a tangent rather than a secant and that this distance is B. Then these two segments have the same length, and now A times C equals B times B, or B squared. So as a final challenge, suppose this segment has length 6 and this chord between these 2 points on the circle has length 4. So notice you have not been told the length of this segment from the intersection to this point down here, although you can figure it out. And suppose this yellow segment has length 5. See if you can figure out the length of this green chord over here. And if you get stuck, feel free to ask for a hint.